Okay, this is our little lesson on electromagnetic induction, mentioned in one of the later videos when we talk about transformers, but we'll just go through it again here, and we're going to know what it is, be able to explain it, and also know one of the uses of induction, which is the transformer later on. But for today's lesson, we're going to talk about the microphone. Okay, so what is induction? Well, this is the whole idea of induction. If we have got a magnet and a coil of wire, and if we move the magnet into the coil of wire, we'll just sort of do that. Then you can see on our milliammeter we generate an electric current. Okay, so if I just do that again, if we move the magnet, when there's movement we generate an electric current. Now as soon as the magnet stops, the current stops. So the current is induced by the movement of the magnet through the coil of wire, or indeed you could move the coil around the magnet. It doesn't matter which one moves, okay? As long as there's relative movement between the coil of wire or the wire and the magnet, you do get induction. And this is to do with that the coil of wire is actually cutting through the lines of what we call magnetic flux or magnetic field lines, okay? So what will happen when the magnet moves back out the coil? If we click move magnet, hopefully you've noticed there is a negative current. So a positive current when we moved it in and a negative current when we moved it back. So we get a current in the opposite direction. Okay, so our general idea is that when the magnet moves we get a current. The direction of the current depends on the direction of the magnet movement, and when the magnet's stationary there is no current. All right, so you can keep seeing, sorry if I go back, you can keep seeing the idea. Positive current, negative current. And all throughout your physics, your study of physics, when we've talked about what an electrical generator is, well, this is exactly what an electrical generator is, and we are going to come on to generators in the next lesson. And a generator is how we generate electricity from moving coils of wire and magnets together. Okay, so a bit of a summary. When a wire moves through a magnetic field, a voltage is caused in it. This voltage can cause a current if it's a complete circuit, and this is called induction. This can be shown with a coil of wire and a permanent magnet, just like you've seen. Either object can be moved. We can have a bigger voltage if we move the magnet faster, if there are more turns on the coil, or if a stronger magnet is used. And remember to say stronger, not bigger magnet, because you can have a big weak magnet and you can have a small strong magnet. The voltage produces in the opposite direction if the direction of movement is reversed, or the coil's turned round, or the magnet's turned round. So any kind of change that causes a turning round of the magnet or the coil, or the movement changing round, that will produce current or a voltage induced in the opposite direction. And remember, very often you talk about induced voltage, but an induced voltage will cause a current to flow if there is a complete circuit. Okay, so what we're going to talk about now, the extension box, we're going to look at graphs to show how the voltage is changing. So here we go, we're moving a magnet into a coil of wire, and if we had an oscilloscope connected to it, let's have a look what we'd see on screen. There's the movement, and as the magnet is moving through the coil, we get a voltage on screen. Okay, and it seems to have gone up like 1.5 squares-ish, something like that. Okay, so I'll do it again. So we get a positive. Now, what's going to happen if we now move the magnet twice as quickly into a coil? Well, if we move it twice as quickly, there you go, we get a much bigger voltage. We get a twice as big a voltage, but notice, because we're moving it twice as quickly, this voltage only lasts for half the time. So the width of this is only half of what it was. If I go back to the first one, here is a much longer period of time where the voltage is being produced, but it's a smaller voltage. If we move it in faster, it's a bigger voltage, twice as big, but it only lasts half the amount of time. Okay, then we could do magnet moves slowly into a coil, but the other way around. So now it's not the north pole that's first, it's the south pole, and you should be able to predict. There you go, we've got a long negative voltage induced. So this is opposite to the very first one that we did. Okay, so let's do that again. So as it comes in, it's now negative when there's movement. And if we did it move slowly into a coil, the final one, a magnet moves slowly into a coil with twice as many turns. And notice we're back to the north pole. So if we've got twice as many turns on the coil, let's have a look. It's slow, So we get a nice long trace, but because there's twice as many turns, that has doubled the amount of voltage we get out. So here you can see we've kept the speed the same, slower, but we've doubled the turns, so that has increased the voltage. So the number of coils, or the number of turns I should say, on the coil, and also the speed of movement, as we said in our summary, this is what affects the amount of voltage that is induced. Okay, so we'll do another one. Magnet move quickly into a coil with twice as many turns. So if we've now got twice the number of turns and we're going to move it quickly, let's have a look what happens. Oh my gosh, you can see it's a bit silly. We go off the screen. So the time is halved. So this is only half the amount of time for the voltage, but look at it, it's huge. It really has increased. It's doubled up again, because not only have we doubled the coils, we've also doubled the speed that we moved the magnet into the coil by. Okay, so microphones. What on earth has a microphone got to do with this? Well, a microphone, this little animation is showing us, is a coil of wire in a magnet, and when you talk into a microphone, the sound waves, the high and low pressure sound waves, cause the cone, if you like, or the microphone surface to vibrate, and that surface that vibrates is connected to a coil of wire, and the coil of wire vibrates, and the coil of wire is in a magnet. You can just see this big circular thing here as a magnet. Okay, so the sound waves cause the coil of wire to move or vibrate in a magnetic field, and just like we've seen, this makes an electric current flow in the wire. So in this wire you get electricity being produced, and the amount of current produced depends on the volume, that's how loud you shout, and the frequency of the changing current. Okay, so the amount of current depends on the volume, and the frequency of the current depends on the pitch of the sound. So how high or low your voice is will change the frequency of the vibration. How loud or quiet your voice is will affect the amplitude of the vibration. And so the loudness will affect the amount of current, the frequency or the pitch of your voice will affect the frequency of the current. So what microphones are doing, they're converting sound energy into electrical energy by the process of induction. And then what you would do, you plug an amplifier into this, and an amplifier takes the signal from the microphone and just makes it louder. Okay, and we looked at the loudspeaker in last lesson. So just to finish, in summary, how a microphone works: sound waves hit a flexible diaphragm that is attached to a coil of wire. The coil of wire is wrapped around a magnet. This causes the coil of wire to move in a magnetic field, and we know that this generates an electric current, which is called induction. And the louder the sound, the more the coil moves, the greater the induced current, and the higher the frequency of the sound, the higher the frequency of the changing current that is produced. Okay, so again, it's all using the idea of movement of a coil of wire in a magnetic field.